Okay, we're gonna continue on here. Little lecture, then a little break, and then a little exam, then some weekend, and all that good stuff. So, we are in the never-ending chapter 14, and obviously we've been talking about pH in this chapter, and I believe last time we got into sort of the pH here of weak acids. And remember that because they're weak acids, they basically will set up an equilibrium. If we just look at a generic sort of acid here. And because they'll set up an equilibrium, you could write a K expression for that, which is known as the Ka for acid there, acid dissociation constant. And really, as we talked about before, regardless of the little subscript there, they're all really equilibrium constants. So you could write a normal sort of equilibrium expression. Obviously, like normal, anything that is solid or liquid would be left off. So if you did have an equation or you did write the equation with water for the dissociation of the acid, you would obviously leave the water off. And because they are weak acids, we cannot just get the H plus concentration directly from them like we could do with a strong acid. So we also talked about, I think at the beginning there, strong acids, something like HCl. And because it is a strong acid, it will 100% break apart or ionize in solution. And because you have 100% of that, you're able to sort of directly from the concentration of the whole thing related to the concentration of the H plus, and obviously you're able to go directly into really your pH equation. But in the case of our weak acids, because they do set up this equilibrium, we do need to ice table up this reaction. And it is just like our normal sort of ice tables that we did in the previous chapter there. We would go through it all. We would have usually zeros on this side, some type of molarity minus X, plus X, plus X, and obviously a molarity minus X, X, and X. Just like normal, we would go into our expression there. We would solve for X, and we could solve for X again the same way we did in the equilibrium chapter, because it really is just an equilibrium problem here. And again, if you can do a perfect square, that's good. If you have to do the quadratic, then you need to do that. Or again, if you can make the assumption, you could try the assumption as well. Remember, we did a couple there with some assumptions, and sometimes it does work, sometimes it does not work. So you should always check your assumption if you make it. Again, you can only try the assumption if your obviously K value is a relatively small value. So that's really the only place where you should try the assumption to see if it works. The main difference here is really in this case, a lot of times we're just interested in what the H plus concentration is, and that usually is the X value. And once you get that, then at that point you can go into your pH equation there and calculate the pH. Any questions on any of that stuff there that we talked about last time? Okay. All right, so we are continuing on here and to talk about another sort of idea of acids, and that's what's referred to as percent ionization. And percent ionization um, is the ionized acid concentration divided by the initial acid concentration times 100%. So it's basically the H plus concentration divided by the initial concentration times 100%. The calculation for percent ionization is essentially the same calculation that we do for our check when we make the assumption. So when we do the assumption, we're really doing this calculation here. When we check it and we divide by the initial concentration, this will give us the kind of, if it's 5% ionized or less, it's all good. If it's more than that, then it's a significant amount of change. So this is really the checking part of that assumption that you make is here. Obviously here, if we have some type of strong acid, it is going to 100% break apart in solution and become 100% ionized. And again, all you will have in that solution is a bunch of H pluses floating around along with some A minuses, whatever the negative guy is. And again, that's really why that is a strong acid, because it will produce a lot of free H plus really quickly. And again, that's obviously a definition of an acid is the ability to produce H plus. So when it completely breaks apart, there is none of the whole unit still together. That's different than a weak acid. Again, a weak acid is going to really mainly stay together. So different in that solution, you're going to mainly have the acids still together, but will break apart a little bit and produce some ions. And again, because it's still able to produce some H plus ions in solution, it's considered a acid, but it will not produce anywhere near, again, the sort of amount of acid or H plus that a strong acid would do. And we see sort of what I was talking about earlier on a couple of examples, or that pizza example of the whole pizza. You take one slice versus you got like two slices left and you take one slice. And the percent ionization is related to the initial concentration of the acid. So you can see at really low concentrations, we have a pretty high percent ionization. And that's the idea of like, you started with two pieces of pizza and you took one away. It's a greater percentage of what you started with, basically. So you have a lot more of it ionizing. So even though a little bit of the H plus is coming off, that little bit is big compared to what you started with because you didn't start with a lot. We see a dramatic sort of drop in percent ionization as the concentration increases, and that would be more like you got a full pizza and you took one slice out. It's not as big a percentage at that point. And so we'd see a much lower percent ionization there. That is also why concentration effects, for example, when you do your check and your assumption, is it good or bad? And that's what we saw, for example, on the first one we did there, where I think it was 0.5 molar for the first one we did, where the assumption was good. But when we dropped it to 0.05 molar, the assumption was bad. And again, because the concentration was much lower in the second one, even though it's only a little bit coming off, it's still, again, a greater percentage of what we started with. So if you need to calculate percent ionization, that's what you would do. You would want to figure out how much H plus came off free at equilibrium, divided by the initial concentration, times it by 100. So let's take a look at this one here. We have a solution of 8 molar formic acid, and it is 0.47% ionized. We're looking for what the Ka value here is for formic acid. So one thing that we know for sure when we look at this problem is if we're looking for a Ka value, formic acid is what type of acid? It should be a weak acid, right? So we're looking for a Ka value. So that helps us sort of understand perhaps how we should try to approach this, which is maybe we should do some type of ice table happening there, right? So whenever you have any type of equilibrium, you want to do the ice table. So why don't we start with that? We could start with the formic acid, which will break apart and ionize in solution into H plus and a little formate, perhaps. And we can now also write, obviously, our Ka expression for it, like normal, which is our products divided by reactants here. So we could even, kind of approach this like a normal sort of problem. We could do our ice table here. And if I initially started here, I obviously have 8 molar of this guy. And we don't have any information about these guys, so we could assume it's 0. The change here would be minus X, plus X, and plus X. That means at equilibrium, we will end up with 8 minus X, X, and X. Any questions on that so far? So normally what we would do, right, is at this point, once we kind of did our ice table, is we would take these guys and put it into here. Problem is, in this case, we don't know what that number is, and that's what we're trying to basically find. So we need to sort of figure out a way that we could find the Ka with obviously not using the Ka to do so. And that's really where the other piece of information here comes into play, which says that this guy is essentially 0.4% ionized. So we could use our percent ionization formula that we just saw, which equals the H plus concentration at equilibrium, basically, divided by the initial concentration times 100%. So what we do know is we do know the initial concentration, which is 8. We do know the percent ionization. What that's going to allow us to figure out is how much H plus there is basically at equilibrium. And that's important because if we follow our ice table here, that is essentially a pretty good thing to know because that will give us our X value here, right? So we could do that calculation. If we do that, we have 0.47% ionized equals our H plus concentration divided by 8 molar times 100%. So we're going to multiply by 8, divide by 100, I hope. 0.47 times 8 divided by 100. That is going to give us an H plus concentration at equilibrium of 0.0376 molar. Questions on that there? Once again, that's really important because now I can connect my arrow. That, if we follow our ice table, is pretty much what the X value equals in our ice table. And that X value, as we hopefully know, is pretty much all these X values that we have here in the table. So now we can really figure out what is the equilibrium concentration of everybody. And if we do that, obviously this will also equal the concentration of HCOO minus, as that also equals X. We can find the concentration of our acid at equilibrium by taking our 8 minus our X value, which was 0.0376 minus. And that will get us here 7.9624. So now we do have at equilibrium the concentrations of everybody that we need. So the last thing that we could do here is basically figure out the Ka value by plugging those numbers in. And if we do that here, our Ka will equal basically 0.0376 squared, as these are both the same number, basically, divided by 7.9624. And there that is. And that will give us a Ka of, if I punch the right number in, probably give us a better Ka value here. Try that. Divided by that. All right, that gives us a, we'll call it 1.8 times 10 to a lot of zeros. Let's see here. 1, 2, 3, 1, 2, 3 minus 4. Here, I believe, if I count that right. 1, 2, 3, 4. Yep. So here's an application, obviously a percent ionization, where we could actually use it to sort of back calculate the concentration of each of these guys at equilibrium, and then that will give us our Ka sort of value. Any questions on that? You obviously as well could just do a straight up percent ionization, plug and chug it to the equation and figure out what the percent ionization sort of value is. Any questions on that there? So we've talked about weak acids and how to approach those problems, but obviously as well, we could have some weak bases, and we could do some weak base calculation as well. Not surprisingly enough, a weak base is an equilibrium, which means we can write an equilibrium expression here. And I will say, as I might have said before, people sometimes struggle with writing the equations for bases. You definitely probably want to include the water in those equations. It sometimes just helps you with it. It allows you to kind of see perhaps that guy's going to send over the H plus in that case. But because this is an equilibrium, we could do our products over reactants. This is oddly known as a Kb value, which means base, obviously. So that's the weak ionization constant for a weak base. The same idea as the weak acid, which is as the Kb value increases, so does the strength of the weak base. And it's for the same reasoning. And the reasoning there again is if we have a larger value of K, That means that equilibrium, we should have more products, which means if we have more products, we have more free OH minus, which will make it a stronger base, as that's the definition basically of a base is something that's able to produce OH minus in solution. Obviously, again, just like in the weak acid comparison, when we're talking about the weak base, we're talking in terms of comparing a weak base to another weak base, the strength of those guys, you would compare the Ka-B values. For our strong bases, obviously they would be much stronger than any weak base because all they have to do, like something like sodium hydroxide, is again go for a swim, and it's going to completely break apart into ions and produce a lot of OH minus really quickly. So again, a strong base much stronger than a weak base, and we can compare the strength of weak bases by looking at the Kb values. Now, when we talk about Ka values for weak acids and we talk about Kb values for weak bases, would we find a Ka or a Kb value for a strong acid or strong base? Typically speaking, the answer is no. And the reason it's no is because it does not set up an equilibrium, right? It's a strong electrolyte, so it's going to completely break apart into products. There's really nobody going back the other way to create that equilibrium. So we do not see Ka values or Kb values with strong acids or strong bases because they really don't set up an equilibrium. So again, these are things that you want to think about as you go through problems, because definitely you see a Ka or see a Kb value, you know for sure that you're dealing with a weak acid or weak base, and you should be doing some type of ice table in that sort of calculation. We pretty much approach these weak base problems the same way. You're going to do an ice table. The difference here is when you do solve for X, you do have to remember that you are dealing with a base, which means X in this case, when you do solve for it, is actually the hydroxide concentration, is not the H plus concentration. So that usually will mean that you will be going into the POH equation first, obviously to get your POH value, and then you could very simply use that the pH is equal to 14 minus the POH. So there's that additional step. And again, sometimes people do sort of mess up on that, kind of going quickly at it. You just have to remember that, again, that unlike a weak acid where you do get the H plus concentration, here you will get the hydroxide concentration. So you got to kind of take that POH route first, followed by the pH. Do all the same things, either assumption, quadratic, however you want to solve it, should work out the same way. All right. So as the guy's yelling there, again, you get the OH minus instead of the H plus, so POH first. Here's a table. Again, you may have to reference a table for your book to look up some Kb values, and there's some there. So why don't you give it a go here, see what you come up with. We got Kb here for this compound. That's 5.6 times 10 to the minus 4. We want to know what will be the pH of this solution, the C2H5NH2 at equilibrium. So see what you come up with here. Let's take a look, see how we're doing. So again, a couple of things that will help you hopefully focus on what you need to do. Obviously, again, we see a Kb, so that automatically should scream a weak base. Should secondly be screaming at yourself an ice table. Don't scream too much at yourself, but you should end up with an ice table here that we need to do. So we can start with our equation here. So C2H5NH2. And again, as I mentioned, probably unlike the weak acids or acids in general, you don't necessarily have to always put the water in. Here with bases, especially weak bases, it's a good idea maybe to include the water in your equation. Again, hopefully that will help you visualize that the H plus should be heading over there, and also where the OH minus kind of comes from. And all we're going to do basically is just pop on that H plus there on this guy. So we'll call it NH3 plus. And again, that is from the water where our hydroxide obviously will come from. So again, just sort of including that water sometimes will help you get the equation correctly, which you do have to obviously be able to write these equations in this class. So That's a good idea. We could also then write, obviously, our KB expression in this case, which would be our products. So our C2H5NH3 plus, a little OH minus, and here we'll go over our C2H5NH2 just like normal. Going to leave the water out as it's a pure liquid, so it won't go in there. This is going to equal our KB value in this case of 5.6 times 10 to the minus 4. Questions so far there? All right, so we're going to ice table it up here. We have initially 0.15, 0 and 0. Change minus x, and at equilibrium here, 0.15 minus x, and x. At this point, like normal, we could go into our KB expression, and that will essentially give us x squared divided by 0.15 minus x equals our 5.6 times 10 to the minus 4 in this case. It's a small KB value, which means we could assume x is equal to 0. And if you do that and you checked it, it is a bad assumption because it's like 6.1%. If you did check, again, a good reminder that you should check. By the way, when you do check your assumption here, it also is, again, that percent ionization calculation, which means you can use, obviously, the percent ionization calculation we solve for bases as well. So that's essentially what you're doing here. So that means we need to roll it the old-fashioned way, which is probably quadratic-ish. We're going to move that over there and multiply it. So that's going to give us an x squared is equal to something. 0.15 times 5.6 to the minus 4 gets us a 0.000084 minus 5.6 times 10 to the minus 4x. Obviously, we're going to bring everybody to the same side, and that will get us our x squared. That's going to be a plus 5.6 times 10 to the minus 4x. That's going to be a minus 0.000084 equals 0. That's going to be our A, B, and C here. So we're going to go into our quadratic, hope for the best. So let's see. We're going to go x is equal to minus b, so minus 5.6 times 10 to the minus 4, plus or minus the square root of b squared. So we'll go b squared, 5.6 to the minus 4 and square it, minus 4 times a, which is 1, times c, which we do want to take the negative with that. So negative 0.000084. That's going to give us, there we go, 0.000336314 inside the square root. Do a little square root action on it. Going to give us a 0.01834, all divided by 2 times a, which is 2. That will give us 2 x values here. That's going to give us an x value if we go the plus root, minus 5.6 to the minus 4 plus 0.01834 divided by 2 gets us 0.00889. Or if we go the subtraction, that is definitely going to yield us a negative number in this case, which is probably not so great. But we'll get a negative 0.00945. Obviously, here we're interested in the OH minus concentration, which is X, so negative value, not so great. That means here that this X value should equal my hydroxide concentration, which would be 0.00889 molar. Once again, we do want to remember that it is the hydroxide concentration. Whoops, wrong way. Sorry. That is the hydroxide concentration. So we do want to go into the POH first. So the POH minus the log of our hydroxide, 0.008, what I got there, 89. So minus the log 0.00889 going to give us a 2.05 on our POH. Again, at this point, if you messed up in the sense that you thought that that was the pH value, it should not make sense to you, right? Because this is a base. So obviously, if that was like your pH of 2, that should not make sense to you. So we do want to go with our pH would equal 14 minus our POH of 2.05. And hopefully this value will make more sense, like 1195 pH, which is basic and should make sense. So as you can see here, we do approach these pretty much the same way as everything else that's an equilibrium problem. Here, though, we're interested in the hydroxide concentration to the POH to the pH. And again, a subtle reminder, make sure you do check that it's not above 5% ionized. And again, like I said, you can use that percent ionization sort of formula for bases as well. What would go up on top would be the amount of OH minus, right, at equilibrium divided by the initial concentration of the base and times it by 100 if you did it in the basic form. Any questions on that there? So let's talk about a couple of other sort of relationships which are important. So obviously up to this point, we've now seen a weak acid dissociation from our weak acid. We also just had obviously a weak base dissociation, which is our base. If you add those two equations together and cancel out everything, you get this equation, which is our water equation dissociating, which is, as we know, also an equilibrium and Kw. So there's a nice relationship that if you take the Ka value and you times it by the Kb value, because as we talked about before, when we add equilibrium reactions together, you do what with the K values? You multiply them, right? So if you take the Ka times Kb, that equals the Kw. That Kw obviously is the same Kw value that we've been using, which is our 1 times 10 to the minus 14 number. So this is a nice convenient way that if perhaps you only have the Ka value, but you actually need the Kb value, you can get the Kb value pretty easily by using Kw and vice versa. Why would you need to use that? We're going to see some calculations here in this chapter where, frankly, they give you the wrong K value. They give you a Ka value when you need a Kb value, and you have a Kb value when you need a Ka value. So it's very common in some types of calculations that you do that the value that you have given to you is not really the right Ka value. So that brings up a really important understanding of Ka and Kb. How do I know I should be using a Ka value or I should be using a Kb value? What should I see in the equation? Which is why it's important to know how to write these equations. What should I see in the equation on the product side if I am using a Ka value or should be using a Ka value? What should be there? I would say this guy should be there, yeah? H plus, acid, right? Or H3O plus if you're using water. H3O plus or H plus that's on the product side of an equation that you write correctly or have, that telling you your acid all day, you should use your Ka value. Same thing with the base type thing. If you see hydroxide there on the product side, yeah, probably should be using a Kb value. So that's a really important understanding. Sometimes people just gloss over that part. Again, also why it's important to make sure you're able to write these equations correctly so that you know when you write it and you write on this side you have H plus, you're actually producing H plus and it's not supposed to be OH minus. So that's an important aspect of it as well. But if you see H plus or H3O plus on the product side, and it's a weak sort of problem, you should be using a Ka value. And if you see hydroxide there, you should be using a Kb value. Any questions on that? Yeah. Okay. All right. So obviously here we can use the Kw, and it's basically the same calculation. You're just going to take 1 times 10 to the minus 14 and divide it by either the Ka or the Kb to get the opposite value. So let's talk a little bit about acid strength and ways that we can look at acids and sort of determine, if we're comparing a couple of acids, which one might be a stronger acid versus one that might be a weaker acid. So the first type of acid is sort of non-oxygen containing acids. So when you have acids that do not have oxygen in them, one thing that you might think that you would look at is electronegativity values of the negative guy. And actually, in the case of acids that do not have oxygen, actually, the major thing that we look at is bond enthalpy. Perhaps you remember bond enthalpy when you maybe did bonding in Chem 50, where you like add up all the bonds you broke and all the bonds you made and like subtract them and get a delta H value based on bond enthalpy. Double bonds, triple bonds, single bonds. But we do look at bond enthalpy, and what we see actually in group 7, where we look at the comparison of basically these acids, what we see is in terms of bond strength, we see the strongest bond energy happening with HF and actually the weakest there with HI. So that's really important because basically, if we take a look at HF, right, or even HI, right, what makes it an acid is the ability of these hydrogens basically to pop off. And the only way it's going to pop off is you got to break that bond. So because this guy takes a lot more energy to break that bond, it's going to come off a lot less than, say, the HI, which is a lot less energy to break it, right? HI, you look at it, and it's just going to pop off because it doesn't take as much energy compared to HF. So because of that, because bond enthalpy increases as you go up the group in group 7 for our acids there, we actually see acid strength decrease as you go up. And that's why HF, which has a relatively strong bond energy, is the weak acid, and as we go down, these guys are actually stronger acids because it takes less energy to break off that H plus and let it be free in the solution, because that's basically the idea there. You want to separate the H from the F in that case and allow it to then be freely floating in the solution. Any questions on that there? So in comparison of acids, kind of almost like group 7 acids, if you will, you want to look at bond energy is your major determiner of bond strength. Now, when we're dealing with acids, so obviously in this case, HF is much weaker acid than those guys coming down. When we look at acids that actually do contain oxygen, and here's a table from your book, and as you can see, heading that way to the right, and down is stronger acid strength. When we look at acids that actually do contain oxygen, these are sometimes referred to as oxyacids, and that's because they contain oxygen basically. And for the most part, most oxyacids will have this bond here, the OH bond, which is a polar bond. Yeah. And that helps it release the H plus, and that's the H that comes off. So it is this hydrogen off that OH bond in these acids that actually pop off in solution and become basically the H plus is free. Like acetic acid, this guy here, for example. This is what acetic acid, like in vinegar, looks like. And it is that H that basically pops off to make acetate and H plus floating around in that solution. So when we look at oxyacids, there's really two things that we look at, and it sort of depends on the situation. One thing that we look at is the center atom, and the one is sort of attached to that OH bond. And we look at the electronegativity value. Electronegativity, again, is that ability to bring electrons towards itself. It increases right as we go this way on the periodic table, right? And decreases as we go this way, with fluorine being the most electronegative, right? The other thing that we look at is the oxidation state, depending on the situation. Now, the oxidation state you might remember from maybe when you did a little redox conversation, maybe in the previous class. Oxidation state is not necessarily the charge that an element may have. It is sort of the, if you want to think about it, it is kind of like the charge that it takes a lot of times in covalent bonding. based on who it's bonded to and who it's sharing electrons with. So sometimes the oxidation state is not necessarily the ionic charge that you think about for elements. Like, for example, chlorine, we think of as being -1, right? And that is true in an ionic compound because the electrons will fully be transferred over. But when something like chlorine is actually sharing electrons, it could take on more of a positive sort of oxidation state, and it's kind of like a positive charge. So it's not always equal to those ionic charges that we think of a lot of times. So how do we know which one we should look at? So let's take a look at some of these examples here. So if we have these two acids here, and these oxyacids have different central atoms, but basically are from the same group on the periodic table, and they have the same oxidation number, we actually will look at electronegativity. So how can we assign oxidation numbers to know if they do have the same oxidation number? So pretty much oxygen is a -2 oxidation state. So that's usually a good place to start. Since these are oxyacids, they typically will have oxygen in it. That's a -2 for this guy, a -2 for this guy, a -2 for this guy. Hydrogen is +1. So if I add up all that together, that is 2, 4, 6 minuses, and a +1 means I have an outstanding -5 happening. That means in this case, the chlorine has an oxidation state to balance it out to 0 because there's no charge on this molecule, of +5 in this case. So chlorine here actually has a +5 oxidation state. Same thing if we look over here at this acid here, -2 for this guy, -2 for this guy, -2 for this guy, oxidation state, +1. Same deal, we got -6 and +1 is -5. Again, it has no charge, so that is a +5 oxidation state on those center atoms in each of these cases. These are two prime examples of what I was just talking about. Normally, we think of the chlorine and bromine as being -1 when we're talking about ionic compounds, and it is because it will be receiving the electrons. The difference here is it is now sharing electrons with oxygen, which actually is going to probably pull the electrons up. Chlorine in each of these cases to now be more electron deficient, right? As the electrons move away. So it actually will take on a more positive charge in that situation because it's actually sharing electrons with atoms that have different electronegativities that are drawing those electrons away. So in this case, when we look at these acids, which are oxyacids, and they both have the exact same oxidation state, we obviously cannot use oxidation state to determine which one is a stronger acid or a weaker acid. So here we would actually look at electronegativity as sort of the defining thing to look at. And when we look at chlorine and bromine, they're in the same group. Chlorine is more electronegative than bromine, as they are in the same group. What does that mean? Well, to start with, we have a polar bond between the hydrogen and the oxygen, which means if I draw an arrow for my electrons, they're basically heading towards the oxygen. Now, with chlorine being more electronegative, it's going to pull those electrons even further closer to chlorine in a sense. What that is essentially going to do to this bond is make it stronger or weaker as the electrons keep moving away from it. It's going to make them weaker, right? So the farther things get away from it, it's going to make the bond weaker. And that's going to allow this hydrogen to pop off a lot easier than what we see over here with the bromine, because bromine is less electronegative. So it's going to bring the electrons not as far in. And it is going to weaken this bond, but not as weak as, say, this bond will become. And it's going to be harder in relative comparison for the bromine guy in the center there to lose that hydrogen than the chlorine in that case. So in this case, because the chlorine is more electronegative than the bromine, we would think here that chloric acid would be stronger than bromic acid here. Any questions on that? So in the case of an oxyacid, you got same oxidation state on the middle guy. You're basically going to look at electronegativity. The one with the higher electronegativity should be the stronger acid because that's going to weaken that OH bond and allow the H plus basically to come off a lot easier. Any questions on that there? Now, what happens if we have acids or oxyacids where we have actually the same central atom, but different things sort of attached on the outside. So clearly in this case, because they are the same central atom, in this case, they are all chlorine, we cannot use electronegativity to help us decide because they both are, everybody's chlorine, so they all have the same electronegativity. So here we would need to look at oxidation state of our central atom. So if we do our oxidation state, starting with oxygen, which is always a good place to start, -2, and a +1 for the hydrogen, that leaves me a -1, which is why this chlorine has a +1 oxidation state in this case. Coming to our chlorous acid, we have a -2 for this oxygen, a -2 for this oxygen, and a +1 for the hydrogen. That is a -4, and a +1 is a -3. And that is why the chlorine in this arrangement is taking on a +3 oxidation state. Here's the one we kind of just did, I think, on the previous slide, -2, -2, -2, and +1. That's a +6 or -6 and a +1 is why the chlorine here is 5 +5. And lastly, here with perchloric acid, -2, -2, -2, and -2, +1 here for the hydrogen. So our oxygen is contributing basically a -8 sort of charge. Hydrogen is a +1 charge. That leaves you a -7. Again, this is neutral, which means that the chlorine here is a +7 oxidation state. So what we see in terms of acid strength is we have a much larger positive charge happening here with this chlorine. Again, that's going to pull those electrons in closer to the chlorine, once again weakening this bond, allowing that H basically to come off. Much more than what we have over here, where we only have a +1 charge, right? Kind of pulling those electrons in. The attraction of opposites attract is based on the size of the charge, right? The larger the charge, positive or negative, will pull things in closer, right, to each other. And in terms of acid strength, that means our strongest acid would be perchloric acid, followed by chloric acid, followed by chlorous acid, and hypochlorous acid would be the weakest of this group. We also see what I was talking about before when we see the chlorine in this acid here that's only attached to one oxygen. We don't see as much of a pull of those electrons away from chlorine as we do when we start attaching chlorine now to 4 oxygens, which are each going to pull the electrons away from chlorine. Not going to take them in this case, they're still sharing, but because of the difference in electronegativity of those 4 guys pulling on the chlorine electrons, that is what we see here with chlorine taking a much more positive oxidation state in that case versus what we see in hypochlorous acid. Any questions on that there? All right, so the next thing we're going to talk about is actually salts. And we get salts, as you hopefully know, from a reaction of an acid plus a base. And we get a salt and water, right? That is typically what happens. And in the most case, obviously, this guy usually contributes the H plus and the OH minus to sort of make our water. The salt's sort of left over from what it came from. This is where those relationships that we talked about earlier on are really important. And what I mean by that is, if you remember, we talked about sort of an acid and its conjugate base. And if we have a strong acid, its conjugate partner is going to be relatively weak. Yeah. And if we have a weak acid, its partner's conjugate base will be relatively strong. And we have sort of the same arrangement here with our bases. And if we have a strong base, its partner, which is the conjugate acid, is going to be relatively weak. And if we have a weak base, its conjugate partner will be relatively strong. So what do we mean by sort of, again, weak or strong? We're talking about here sort of the ability of the conjugate base or the conjugate acid to continue to react. And that is the salt. So if we think about where the salt's hanging out right now, what is there for it to react with on that side? Water, yeah. And that is what we're going to be looking at here with salts, is whether or not that salt will continue to react with water. And if it continues to react with water, it can have an effect on basically the pH of the solution. So how can it have an effect on the pH of the solution? So if we take a look at, say, a salt, and we have a salt that has the ability to continue to react, and that would be a salt that obviously is relatively strong, and that would be these guys here. And they come from things that are weak, which is, again, an important relationship to understand. So if we have this salt that originated from either a weak acid or a weak base, it has the ability to continue to react with water that's present. And the result of that is, in certain cases, the salt will have the ability to act as a conjugate base, right? Which means a base will accept an H plus from the water. And when it accepts the H plus from water, it will create the salt plus the H plus. But more importantly, what it will produce is hydroxide. And it will be able to produce some more hydroxide from the water by continuing to react with the water that's present. And that's important because that means in my beaker where I have this salt, I now have the salt reacting with water, which is increasing the amount of hydroxide that's in my solution, which means if my amount of hydroxide in my solution goes up, the pH probably should then be more basic, right? So we would expect this to be more basic, or really basic in this case, because we are producing more H plus in that solution as a result of that salt continuing to react with water. Any questions on that? Now, we could also have a salt that can react with water, but maybe it came from a weak base, which means it would be the conjugate acid, and it could also behave as an acid. And the definition of an acid, right, is something that will donate an H plus. So this salt will actually send the H plus over to the water. The result of that is we will get our salt that is minus an H plus. But more importantly, we will produce H3O plus in solution. So now what we'll have is in our solution, this salt reacting and producing a bunch of H plus or H3O plus in solution. And when we have a lot more H3O plus in solution or H plus in solution, that means we should expect this solution to be acidic, yeah? And that is the sort of ability of a salt. It can actually continue to react and have an effect on the pH by reacting with water and either generating more H plus in the solution or more OH minus in the solution that will either make the solution acidic or basic. And those guys come from, as you can see, weak acids or weak bases. So these are the guys that have the ability basically to do that. Now, what about our guys here that come from our strong acids that have partners that are relatively weak? The idea here is they pretty much will not do anything with water. So they will not react with water, which means we will not see an increase in H plus. So we won't see that. We will not see an increase in OH minus. So we won't see that. So those guys are what are referred to as being neutral salts because they do not continue to react. So it's really important to understand that relationship of if you have a strong acid or strong base, it will create a conjugate partner that's a salt that will not continue to react with water and will pretty much produce you a neutral solution. Now, if you have a weak acid or weak base, that means that the salt that they produce will be relatively strong in the sense that it can continue to react with water and either produce more H plus, which would then make your solution acidic, or produce more OH minus, which would make your solution basic. That reaction with water is sometimes referred to as a hydrolysis reaction because you're basically breaking apart water. So that's sometimes commonly referred to as a hydrolysis reaction. So as we will talk about when we get into this, what you want to think about usually when you look at a salt is sometimes a good idea to think sort of backwards about it as to where did it come from? Did it come from a weak acid? Did it come from a strong acid? Did it come from a weak base or a weak acid? And if you can correctly sort of identify where it came from, you can correctly sort of identify what it will be. So what I mean by that is you could go, well, this guy definitely came from a weak acid. That means whatever I'm looking at is going to be his conjugate base. And what helps you when you go to write these reactions is if that's a conjugate base, it should do what a base does, which is accept an H plus when it reacts with water. And vice versa, if you could identify that this salt came from a weak base, that means that the salt you're looking at is an acid. So when it reacts with water, it will react with water as an acid, which the Bronsted definition of an acid is it will donate the H plus over. So again, sometimes it's a good idea to take a moment and think about, where these things come from so that you can, again, write these equations really correctly and end up with the correct thing on the product side. Because it's important here, if I end up with an equation, by the way, like this first one, where I have OH minus on the product side, should I be using a Ka value or Kb value when I do a calculation? I would need to use a Kb value, right? And same thing if I had this equation down here where I ended up with H3O plus on the product side, I should be using a Ka value, yeah? And I told you a second ago that there are problems where they'll give you the wrong K value. These are the problems where they give you the wrong K value. They will give you the Ka value when you need the Kb value, and they oftentimes will give you the Kb value when you need the Ka value. So these are the very common problems where you come across and you're like, I have this K value here, but it's really not the right one that they give you in the problem. So you have to really understand that you have to do that conversion. How do I get to the right one? That is where we use, again, our Ka times our Kb equals our Kw that we saw earlier. So this is where we can use that relationship of Ka times Kb equals the Kw. And we could very easily get the right one we need. But where a lot of people really go wrong is in the writing of these equations. They write the equation and they do not understand that it's an acid or a base, and they end up with the wrong thing on the product side. So you end up with like H plus when you should have OH minus and vice versa. So again, really important in these chapters, as I've been talking about, to be able to write these equations, because very often they will not be given to you. You will just be given the salt, basically, and that's all you'll be given. Any questions on that? Well, with that bright, fun thought of what's ahead,